Hello students and welcome. Today we are going to tackle a very important topic from our Unit 7 Alternating Current. We're going to talk about phasors. Now I know the name sounds a little bit complicated, but trust me, by the end of this session, this idea will be simple, clear and completely exam safe. Chalo, let's begin.
So first of all, what is the problem we are even trying to solve here? Beta, look, adding simple numbers is easy, right? 2 plus 2 is 4. Simple. But in alternating current, we're dealing with quantities like voltage and current that are, well, they're not constant. They are like waves, always changing, going up and down, and adding these kinds of waves, that can get very complicated very fast.
For example, just imagine you have to add these two AC voltages. See how they are out of sync with each other? One wave is at its peak while the other one is somewhere else entirely. Now, if you try to add them point by point using trigonometry, my goodness, it's a long and difficult calculation, and there are so many places to make a mistake. So the big question is there a simpler, more visual way to do this? And of course there is.
To solve this tricky problem, we're going to use a powerful mental picture. I like to call it the searchlight analogy. Once you get this picture in your head, everything will just click into place.
Just imagine there's a big searchlight, the kind you see at big events or functions, and this searchlight is rotating in a perfect circle at a nice constant speed. The beam of light is pointing at a faraway wall. Now don't look at the searchlight itself. Just focus on the spot of light on the wall. What is it doing? It goes up. It reaches a maximum height. It comes down. It reaches a minimum height, and then it goes back up again. It's oscillating, right? Up and down, just like a sine wave.
So here's the crucial connection. This is the whole secret. We can connect this analogy directly to our AC concepts. That rotating beam of the searchlight, that is our hidden tool, the phasor. And the oscillating spot of light that's going up and down on the wall, that represents our AC voltage or current. So you see, the simple steady rotation of the beam is what creates that complex up and down wave. We're going to use the simple rotation to understand the complex wave.
Okay, so that's the core idea, the story behind it. But now, for our exams, we need to get a bit more formal, right? Let's build this concept of a phasor step by step, just like you would in your answer sheets.
Look how simply we can actually build a sine wave. Step 1. We start with a vector, an arrow, and its length is equal to the peak voltage, V0. Step 2. We rotate this arrow counterclockwise at a constant angular speed, which we call omega. Step 3. At any given time t, the angle that it has turned through is simply omega times t. And finally, the most important part, step 4, the vertical projection. You can think of it as the shadow of this vector on the y-axis. Its length is v0 sine omega t. This means the vertical component of this simple rotating vector is what's actually creating our AC sine wave.
And this brings us to the formal NCERT-approved definition that you must write in your exams. So what is a phasor? A phasor is a vector which rotates about the origin with angular speed omega. The magnitude or length of this vector represents the amplitude, like V0 or I0, and its projection on the vertical axis gives you the instantaneous value at any time t. Please, make a note of this exact wording. It's very important.
So we have the definition, we have the core idea, but is it actually useful? Does it make our life easier? Let's find out. Let's use this amazing tool to solve that difficult problem we saw at the beginning. We'll take a very simple example.
Okay, here's our problem. We need to add two voltages. The first one, V1, is 100 sine omega t, and the second one, V2, is 100 sine omega t minus 90 degrees. Now notice a couple of things. They both have the same amplitude, 100, and the same frequency, omega. The only difference is that V2 is lagging behind V1 by 90 degrees.
So how do we use phasors to solve this? Step 1 is to draw a frozen picture of the situation at time t equals 0. For V1, the angle is omega t, so at t equals 0, the angle is 0. Its phasor is just a horizontal arrow of length 100. Easy. For V2, the angle is omega t minus 90 degrees. At t equals 0, that angle is minus 90 degrees. So its phasor is a vertical arrow pointing downwards, also of length 100. See what we did? We've turned those complex, wavy things into two simple little arrows. Now for the best part. How do we add these two arrows? We just add them like we learned back in class 11, vector addition. Remember the head-to-tail method? We just place the tail of the second vector at the head of the first one. The final resultant vector goes from the start of the first to the end of the second. It's just simple geometry, nothing more.
And to find the properties of this new resultant phasor, we use simple maths. The magnitude, or the length, is just the hypotenuse of this right-angled triangle. So, using Pythagoras' theorem, it's the square root of 100 squared plus 100 squared, which comes out to be about 141.4 volts. And the angle phi, you can clearly see it's minus 45 degrees.
So now we just have to convert our resultant phasor back into the waveform. The magnitude we found, 141.4, that's our new amplitude. The angle we found, minus 45 degrees, that's our new phase. So the final answer is V of t equals 141.4 sine omega t minus 45 degrees. See? No complex trigonometry at all. Just simple vector addition. Simple, Henna?
Okay, this next part is very, very important for your exam, so please pay close attention. Let's talk about some silent killers. These are common mistakes and misunderstandings that students often have, which can cost you precious marks.
All right, let's look at the first wrong idea. Many students think the phasor angle is always changing in the diagram. No! The phasor diagram that we draw is a frozen snapshot. It's a picture taken at one instant in time, specifically at t equals 0. The rotation is conceptual, but the drawing itself is static. The second wrong idea is thinking that a phasor is just a different, fancy way to draw a wave. No, beta. A wave shows you how the value changes with time. A phasor is what we call a frequency domain view. It shows only two things, the amplitude, which is the maximum value, and the starting phase angle. That's it. So, to finish up today, let's quickly summarize the key takeaways that you should add to your AC toolkit.
Here are the 4 most important things to remember. First, a phasor is basically a rotating vector that acts as a shortcut to represent a sine wave. Second, its length is nothing but the amplitude, the peak value, V0 or I0. Third, its vertical projection at any moment gives you the actual instantaneous value of the voltage or current. And finally, the most important point, why do we even use them? Because phasors turn difficult wave addition into super simple vector addition. So, we now have this powerful new tool in our hands. The big question is, what's next? In our upcoming topics, we're going to study circuit components like inductors and capacitors, and you'll see that they also create phase differences between voltage and current. So, how will this amazing phasor tool help us analyze those circuits easily? Think about that, and we will find out in the next class. All the best.